Okay. So we have the Hall effect. Okay. Okay. So the Hall effect is basically taking place in the Hall probe, and the Hall probe is basically a device used to measure the magnetic field. Okay. Okay. So we say then Hall effect is taking place in Hall probe. Okay, which is a device, which is a device used for measuring measuring. This is the device used to measure the magnetic field. Right. This is the concept. Now, it basically uses the voltage to measure the magnetic field, right? So, mm, it uses the voltage to measure the field, right? Like the same way as we measure the temperature, right? So we basically not measure the temperature directly, rather we measure the amount of liquid expansion, right? Like if you have the liquid in glass thermometer, like the mercury one. So when you heat it, so that temperature, so due to that temperature, due to that heat, the mercury inside the bulb expands, okay, and it start moving onward, right? And that wherever it stops, so we have written some values, so we read the corresponding values, and that we say that okay, fine, this is the voltage, this is the temperature around the object, right? Or this is the temperature present, right? But over here we use the voltage to measure the magnetic field, right? And the formula that relates the Hall voltage in the magnetic field is V VH. Okay, the Hall voltage is equals to BI over N T and Q. Right. And in this formula, basically, you don't have to remember the formula because they'll give you in the paper, right? In the first page of the paper, right? So I'm just writing down the values, or I'm just writing down help to understand the quantities it has. Okay, and we have N. Okay, and we have these. Okay, so right now, so basically B is a magnetic field. Okay, and I is a current. Okay, and Q is the charge, the value of the charge particle. Okay, which is most of the time 1.6 exponent negative 19 coulombs. Okay, and we have T, the thickness of the conductor, or of the semiconductor. Sorry, semiconductor, and we have the number density. Come on, and we have the number density. Okay, so these are the things that we have in the formula. Okay, and basically, if we take them down. Okay, and that quantity is basic the Hall voltage. Okay, it is not any other voltage. It is basically the voltage, the simple voltage that generated when you have the cross field. Okay, appear around it. Right. I'll show you how. Don't worry. By the way, you don't have to remember this formula. It will be given in your paper. The things that you need to know is this one. Okay. Now, only one thing that you have to understand over here, and that is the concept of n. Okay. So n is basically the number density, right? And you see that Hall voltage is inversely proportional with n, right? So you have a semiconductor and you have a conductor, right? So for the sensitivity of Hall voltage of Hall probe, okay, um, the material used should be semiconductor and not conductor. Okay, this is done. And why this is so? Because as the conductor has as a conductor has a greater n value, greater n value which gives lower Hall voltage. Okay, right? So basically, you can see that we have the Hall voltage that inversely related with n, right? And n will be smaller in semiconductor because it is a semiconductor, right? So it won't have any large number of conducting particles. While in the conductors, we have large number of n, so that gives us the small Hall voltage, right? So that's why we use this one, the second one, right? The semiconductor, right? Now, to understand how it works, Acha, by the way, the T is the thickness of the semiconductor, okay? It is not the time or anything related with time, okay? And I is the current flow through it, okay? Now, I have some picture for you guys. Okay, you can see, okay? So basically, in the first picture, we have the Hall probe, okay, and you know that the Hall probe is measure the magnetic field, okay. So the flat surface over here is basically measuring the magnetic field, right? Okay, not the full Hall probe, but just the magnetic field, the flat surface, okay. This is the first thing, right? But we are connected, we have connected that with a voltmeter because it will going to measure the voltage, not the magnetic field directly. Okay, so we are connecting it with a voltmeter that gives us the voltage, and we know that voltage is directly proportional with the magnetic field rho. So we can find out the relationship, right? So this is the first concept, but the point of interest right now is this flat surface, okay? And imagine that this is that flat surface, this is that flat surface, okay, and the magnetic field is right from like north to south, okay, north to south, right, like this. Okay, so what will happen is basically, or let me just draw one for you. I think it would be helpful for you to understand. Okay, so let's say I have, what if I use this one? Mm, couldn't it be? Let me just try if I can get the things right. Okay, so this is one this is one paste, and if I just copy it down to the other one, okay, so this is the other one, right? And this is the other one. Okay, so imagine, okay, so imagine that these are the four dimension of the Hall probe material, okay, and the current is being flowing through it, okay. Why the color is different? Wait, no, okay, fine. So let's say I have the wire, okay, and there's a current flowing in it, right? So what will happen? And it is basically placed in under the magnetic field, okay? So the magnetic field is like this, right? Like this, like this, and like this, right? So the magnetic field is into the page or into the plane, right? Now the current is flowing, like the electron is flowing that way, the electron is flowing that way, right? So can you guys, acha, and the thickness is supposed to be this length, okay? This is going to be the thickness. This is going to be the thickness, okay? Because in most of the questions they'll ask you what is the thickness right here, right? This is the thickness. Okay, so this is the thickness. The magnetic field is there, okay, and it is moving, it is flowing towards the ground, okay. The electron is also moving. So can you guys tell me in which direction should the electron deflect, okay, due to the magnetic field? Using the left hand rule, please. Yes, anybody? Any idea?
Sir, could you repeat the question again?
I'm asking that I have the magnetic field mentioned, okay, and the electron direction is also mentioned, okay, right, and I'm just asking in which direction should the electron deflect if you use the Fleming's left hand rule? Is any idea? If you use the Fleming's left hand rule, so basically the first finger should be downward. Okay, the second finger should be in this direction. So when you open the thumb, so you will see the electron will start gathering right here, right? This is where the electron gathers. Okay. And on the other side, the positive charge will appear, right? Because if there's one place getting negatively charged, so the other plate would be positive charge, right? So over here we'll have the positive charge and positive charge till the end, right? This causes the electric field to be created around, okay, and the electric field will be in this direction. Okay, so this is the direction of the electric field. Okay, the direction of the magnetic field and electric field you can see are perpendicular, right? So we have the magnetic field, we have the electric field generated, okay, between the two faces, okay, and these are the two faces, right? This one, okay, this one and the other one, right? So basically, these are the two faces in which or where the Hall voltage will be created, right? So this is the first thing, and then the second thing, right, like this, okay, and there the Hall voltage will appear. Clear, perfect. Right, and this is the hot voltage VH, VH, right? So the whole voltage will appear across the two faces of the semiconductor, and the magnetic field is perpendicular, so the electron will pass undeviated, right? So if I try to draw the horizontal, or let's say the top view, so the top view would look like this. Okay, so and the electron is entering in this direction. This is the direction of the electron entering. Okay, and okay, and we have the cross dot sorry not dot cross magnetic field. Okay, cross magnetic field. In that cross magnetic field, basically helping us determining the direction. Okay, so you can just have it here and have it here. Okay, so yes, so basically the electron will start appearing onto this side, not outside, inside. Okay, and in return there will be the positive charges at the other end. Okay, so the magnetic field and the electric fields are now in the opposite direction, or basically in perpendicular to each other, right? Right. These are the electric field line, and the magnetic field line is going to be straight, and it will be perpendicular, right? So the electron will start deflecting in this direction when it enters, and when fully all of the electron on the right hand side and the left hand side are equal in number, right? So there will be a strong magnetic field in between the plates, okay, and the particle go undeviated, right? So the particle go undeviated like this, right? And we have discussed this in yesterday's lesson, that if you increase the mass, if you increase the charge, it won't affect any when it is under the mm, velocity selection concept. Okay. So basically, in exam, they'll ask you they'll mention all the edges in the corners of the diagram. Okay, the one on the left hand side, this one, right? Let's say A, B, C, D, and E, right? All the are the points are mentioned, right? So they'll ask you which two surfaces or which 2 points will the electric field form, right? So you have to mention this one and you have to mention that one, right? And that's it, right? And between these 2 points, there will be the Hall voltage, right? That's it. Okay, this is the last concept. This is in very short detail. Okay, so let me take you to the questions and then we'll do some of the question and then we'll end the class. And this chapter is, by the way, completed. A2, where? Okay, I have this. Okay, so everything from this is now completed. Right, now let's talk about some of the questions. I just want you to try from 14, nope, 16. Okay, try this one. Hmm, the magnetic field. Okay, try this one, Mr. Irfan, can you read the question?
Okay, sir. The particle of charge plus q and mass m is traveling with a constant speed of 1.6 into 10 to the power minus 5 meter per second in a vacuum. The charged particle enters a uniform magnetic field of flux density 9.7 into 10 to the power minus 2 t, as shown in figure 9.1. Particle, okay, wait. The magnetic field direction is perpendicular to the initial velocity of the particles and perpendicular to and out of the plane of the paper. The uniform electric field is applied in the same region as the magnetic field, so that the particle passes undeviated through the fields. State and explain the direction of the electric field.
Okay, direction of the electric field, right? So we know that the direction of electric field will going to be same as the direction of electric force, first thing. The second thing, what will be the direction of electric force? So it will be opposite to the direction of magnetic force. Okay, and what will be the direction of magnetic force? So it can be figured out using the Fleming's left hand rule. Okay, so apply the next left hand rule over here. So we have the positive charge, so our second finger should be in this direction. Okay, and we have the dot field, which means it is coming out of the plane. So use this one. Okay, and then the charged particle will go in the downward direction like this. Okay, like this. Right. So this is how, and then it will just get out. Okay, be very careful. They'll give you 3 mark for that. Okay, you have to mention the correct path. Okay, correct starting and ending point and correct direction. Okay, so starting part should be parallel to the given path, right? The mentioned thing, and then as you move in the magnetic field, you have to turn right. So okay. Now, so basically, they're saying explain the effect of the direction, explain the direction of the electric field. Okay, so basically, the charge is experiencing, or the charge would experience the magnetic force in the downward direction, right? Generally, because if the magnetic field is coming out of the plane, then the first finger will be towards the top of the ceiling. The second finger should be rightward because the charge is moving from left to right and the force is downward, right? So, in order to overcome this force, you have to apply another force in the vertical direction, okay? And that should be equal to E times Q. So, yes. So, basically, Okay, it remain in the same direction. Okay, as a magnetic field, as sorry, as an electric force, right? And then we say that the electric force. Okay, so the electric force is in the same direction. Okay, and that is upward, right? So we want the electric force to be upward, and the electric field should also be in the upward direction, right? To get the magnetic field in the same direction, right? Okay. So they're saying calculate the magnitude of the electric force or electric field. Show you're working, right? We know that since they're asking for the show you're working, so we know that magnetic force FB is equals to magnetic electric force FE, right? So the magnetic force is the formula KQ or BQ. So
QE, right?
BQV, yes. And for the electric force, we have EQ, right? So V, Q and Q got cancelled. So B over E, sorry, E over B, come on, B over E, oh no, no, E over B is equals to V, right? So they have mentioned
Sir,
the, hmm
we're finding electric field strength, no? Velocity.
yes, you can just multiply. You don't have to show this one, basically. 9 point, I think 1 or 2, they have mentioned something 9.7 exponent negative 2. Okay, fine. 9.7 exponent negative 2. Okay, this is B. Velocity is 1.6 exponent 5. Okay, and that is equal to E. How much?
15520.
15520. Fine. So that is the electric field strength, right? Okay, please move on.
The electric field is now removed so that the positively charged particle follows a curved path in the magnetic field. The path is an arc of a circle of radius 4 centimeters. Calculate for the particle the ratio Q over M.
Hmm. Which formula you use? Can you tell me? Yes.
Uh, I, I think you can equate it to like the centripetal force.
Okay, very good. So it is BQV is equals so BQV the first formula and then FC is equals to MV square over R, right? And we can say that FB is equals to MV square over R and MV squared, sorry, BQV is equals to MV squared over R, right? And then just cancel out the V and V. And since we're interested in radius, so mass of the charged particle I think is given. Okay, so calculate. Okay, fine. So basically we're interested in charge over mass. Okay, so not the radius. Q over M, and then V remain in that side without any squared, and M remain B and R, right? This is the thing that remain, okay? So you can now use the velocity, which is 1.6 exponent 5, okay? Mass of the magnetic field is 9.7 exponent negative 2, okay? And the R is going to be 0.04 meters, okay? How much? Yes, Irfan.
Just 1 second. 4.1 into 10 to the power 7.
4.1, okay. Exponent 7. Cut. Okay, please move on.
The particle has a charge of 3e, where e is a elementary charge. Use your answer in C to determine the mass u of the particle.
Hmm. So, mm, okay. So basically, Q over M is something that we found out, and that has a value of 4.7 or 1? 4.1. 4.1 exponent 7, right? And come on. Okay, and basically we have charge given as 3e, where e is the elementary charge of 1.6 exponent negative 19. Okay, and the mass is supposed to the mass is something that we have to find out, right? Now, so charge is okay. How much? Wait. So we have 3 into 1.6 exponent negative 19, and then divided by 4.1 exponent 7 gives me m. How much?
1.2 into 10 to the power minus 26.
Exponent negative 26. Okay, so you're saying 1.2 exponent negative 26. Okay, we know that one U has a mass of 1.66 exponent negative 27. Okay, so in U, you just need to divide the value by this one. Okay, and you'll get the answer. Yes,
7.05.
very good. So 7.0. Okay, please move on.
The particle in the nucleus of an atom. The particle is the nucleus of an atom. Is okay. State the number of protons and the number of neutrons in the nucleus.
Hmm. So we have found out the mass number. Okay, 7 U. Okay, and we know that the charge that it contains is 3, okay, electron. So proton is supposed to be 3 as well, right? And neutron is going to be 4, right? Making sense?
That's a
Yes.
very good. Where do you get the three from? The
3
proton.
is basically here. The particle has a charge of this much, okay? So this
Oh,
means
okay,
it
fine.
has it had that 3 electron that it is now being lost, okay? Okay, fine. So Meghnad, can you please read this question?
Then rectangular slice of aluminum has size of length 65 millimeters, 50 millimeters, and 0.1 millimeters as shown in figure 9.1. Some of the corners of the slice are labeled. A current I of 3.8 amperes is normal to phase RSXY of the slice. In aluminum, the number of free electrons per unit volume is 6.0 times 10 to the power 28. The uniform magnetic field of magnetic flux B equals to 0.13 P is normal to phase QRYZ of the aluminum flux in the direction from Q to P. A whole a whole voltage is developed across the slice and is given by the expression.
Okay, now please move on to the first one.
Use figure 9.1 to state the magnitude of the
Hmm.
density.
So basically, it is supposed to be the thickness, right? So can you tell me the thickness, please?
0.1 millimeter.
Very good, very good. 0.10. Okay, fine. Please move on.
Calculate the magnitude of the whole voltage.
Hmm. So for that, we can use V is equals to BI over the magnetic field is mentioned as 0.13. The tension is, sorry, not the tension. The current is mentioned in 3.4. 3.4 or 8? Yes, 3.8. Okay. The N is supposed to be 6 exponent 28. So T is, by the way, zero point 0.1, zero point 0.1 exponent negative 3. Okay. T, and Q is supposed to be 1.6 exponent negative 19. Yes. So can you find out the value, please? Yes, any value? Anything you're getting?
5.1 times 10 to the power minus 7.
Okay.
5.1 times 10 to the power minus.
5.1. Good. 5.1 exponent negative 7. Good. Okay. Similar question, right? Now they're saying state what is meant by N. So you know that number density of the charge carrier, or they've mentioned N is the number of the free electron per unit volume. Okay. And then we have the symbol T represent the thickness, right? You can look at the picture and you can quote it the value, right? And then in general, the Hall voltage produces a slice of the material is very small. For a slice of the same dimension with the same current and the same flux density, the Hall voltage produces semiconductor would be much larger, right? So we discussed that for the semiconductor, we first know that Hall voltage is inversely proportional to N, right? Where N is a number density or number density of the charge carrier per unit volume, right? Or the number of electron ejected per unit volume, right? So if we have greater number of electron, then lesser Hall voltage will be produced, and if we have the lesser number of electron, then higher Hall voltage will be produced, right? So this is what you have to mention, right? So an easy one. Okay. Actually, by the way, this second part is not a part of syllabus anymore. So if you come across any such question where they're asking for the holes, okay, so you can ignore it, right? Okay. Irfani. Ibrahim, your turn, please. Can you read the question?
Explain what is meant by a field of force.
Hmm. So we say that the field of force is supposed to be field is supposed to be the region, okay, where a charged particle can experience a force, right? And if it is like related with the magnetic field, then the charged particle should be moving, but it is not. They're not asking that way, so we can just say, okay, okay, wait. Okay, so we can say
Sir,
that.
if you write a region of space, it's also like accepted, right? Region
Yeah,
of space. Okay.
region of space where charge or mass, right? Or you can just say the particle where the charge or mass experiences experiences the force. Okay, it can be gravitational force, electric force, or a magnetic force, right? Okay, please move on. Yes, Irfan. Irfan, no, Ibrahim.
State the type of field or fields that will give rise to a force acting on an unmoving uncharged particle.
Uncharged particle. Okay, so uncharged particle is the gravitational field, right? A stationary charged particle is for the electric field, and a moving charged particle at an angle to the field or field, so it is a magnetic field. Okay.
So इसमें दोनों
Mm-hmm.
आएंगे ना, magnetic and electric.
Um, it is basically it can contain all of the three things, right? Because in the first one, the stationary charged particle experiences the electric field as well as the gravitational field. So let's say gravitational field. Okay, and yep, we can include these two as well. Good. Okay, please move on.
An electron mass m and charge minus q is moving at a speed v in a vacuum. Enters a region of uniform magnetic field of flux density b as shown in figure 7.1.
Okay, so we have the negatively charged particle. Okay, and they didn't mention the direction of the field yet, right? So fine, but it is moving downward. Okay, we can figure out we can figure it out the direction of the magnetic field. Okay, so your second finger should be in this direction, right? And your thumb should be in the downward direction because the charged particle is bending rightward, right? So my direction of magnetic field is basically into the page, right? Cross field. Is that clear, Ibrahim? Chane, please move on.
Explain why the path of the electron in the magnetic field is the arc of a circle.
Hmm. So we have seen that the um as the charged particle enters the uniform magnetic field, uniform magnetic field, okay, with a constant velocity perpendicular perpendicular to the field, right? So the magnetic force provide provides centripetal force to the charged particle, okay, which which causes it to move in the circular arc, right? Okay, please move on.
Derive an expression in terms of the radius r of the path for the linear momentum of the electron. Show your
Hmm. So for show you're working, you can say that the magnetic force provides centripetal force provides centripetal force, okay, and we can say that FB is equals to BQV and FEFC is equals to MV square over R, right? So we can say that only FB is acting as a resultant force, so FB is equals to MA or MR omega square, and then FB can be replaced with BQV. QV is equals to MB square over R. So we get cancelled, and BQR is equals to P, and that is what we have done. Okay, but you have to mention that P is supposed to be MV, right? And yep, that's it. Okay, so we have done some question. Okay, I'm stopping it right here. Okay, your homework is supposed to do all of the question till question number 28, right? But only do those questions that contain this type of charged particle, okay, or this type of question, okay? And please ignore the question that containing the wires, okay, because this is going to be the next chapter, okay, that we have to discuss, right? So like this one, okay? So you have to do this type of question. This one is also solvable, okay? So try these question before the next week, and then after next week, well, inshallah, okay, ignore these type of question, okay? Well, inshallah, do this chapter of electromagnetism, and then we'll move on, okay? So okay, fine, that's it for today, and I'll send you the worksheet, okay? So yep, send okay, take care, guys. Allah Hafiz.
Love it.
Allah Hafiz.